So students, welcome back to part B of today's lecture. Students, we have been looking at the nucleus, and we have not yet started looking at the nucleus. We were just looking at radioactivity and the result of study on radioactivity and what it had revealed. We saw that the radiation that come out from a radioactive material, it's not affected by external conditions, which meant that radioactive rays originate in the nucleus, and that means radioactive rays come out from the nucleus. And how we came to this conclusion? We came to this conclusions because any physical or chemical change does not alter the rate of change of radioactivity. That means radioactivity, it is if active rays, if they are emitted at a certain speed, then they continue to be emitted in the space. We cannot stop it, we cannot control the rate, we cannot reduce its intensity, we can do nothing about it. So if it would have been due to the action of the electrons in the outer orbit, in the orbits of the atom, then we could have controlled it. But since we cannot, I am repeating it again and again because it's a very vital point. And so since radioactive radiation cannot be controlled in intensity or in rate of change, so they are not due to the action of the electrons in the orbits. These rays must have come out from more within the atom. That means they must have originated in the nucleus. So we now can conclude that yes, radioactive rays come out from the nucleus. Now let's proceed further. So again, more studies reveal that radioactive radiation, which consists of different types of rays such as alpha, beta and gamma rays, of which the beta rays are nothing but electrons, and that gave us a certain very interesting thing, because we have already seen that radioactive rays originate in the nucleus, and now we see that radioactive rays are nothing but electrons. So does it not indicate that nucleus contains electrons? So obviously that means the radioactive rays which come out from the nucleus, and they consist of electrons, so nucleus contains electrons. Okay, so this is like one thing leading to the other, and then people came to the another conclusion that okay, if electrons come out from the nucleus, that means the nucleus must contain electrons, and this gives rise to the proton-electron hypothesis of the nucleus. See students, till here, this point, people, when I say people, I mean the scientists actually, they never thought about what the nucleus is made of. They did not bother to think too much about what the nucleus is made of. They thought that okay, it is composed of positive charges, it's okay. By that time the proton was also discovered, so they came to the conclusion that yes, nucleus contains protons, and since radioactivity indicated that electrons come out from the nucleus, so this gave rise to the proton-electron hypothesis of the nucleus. They hypothesized that okay, the nucleus must be composed of proton and electron, and there will be a number of protons, each with charge E, small e, that is the equivalent of the positive charge equal to the charge of the electron, and a minus z number of electrons. So this is called the proton-electron hypothesis of the nucleus. Student, this is an important question from the examination point of view. They often ask about the proton-electron hypothesis of the nucleus. Remember, this is not a theory, it is only a hypothesis. So obviously, if A is a number of protons having positive E charges and A minus Z electrons having minus E charge, then the total charge, the net charge of the nucleus is Z into E. So this is what was the proton-electron hypothesis of the nucleus. But then certain things came up, certain problems. You see how does science develop actually? Actually, some corner of the earth, someone discovers something, and then another person discovers something else, and slowly science is built up. So you see, there are certain points like the finite size of the electron. Then there is again something called the spin consideration. There's again another more advanced thing called the statistics, which is very important in case of quantum mechanical particles. Then there is again the magnetic moment and the uncertainty principle, which we somewhat know. Then there is something called the Compton's effect. I'm sure you're familiar with it, and the Compton wavelength associated with the Compton effect. Then there is the beta decay, and then again there is something called the electron-neutrino pair, which is very important in beta decay. These together, these points, which we will learn in another class, here led to the failure of the proton-electron theory. That means what? The proton-electron hypothesis that was just proposed was proved to be not true, because they could not satisfy these 1, 2, 3, 4, 5, 6, 7, 8 points that I had just shown you. These are points, these are actually experimental points that were found out, observations. So these experimental findings could not be explained by the proton-electron theory. That the electron is a constituent of the nucleus, that was totally found to be wrong, proved to be wrong by each of these points here, which we'll look at in our next class one by one. So for now, we find that this is the failure of the proton-electron theory, and after that, fortunately, the neutron was discovered. Now the question is, why was the neutron discovered so late? So that people have to think about, have to imagine that the nucleus is made of electron and proton. That is because neutron is a neutral particle. So you see, the problem with detecting a neutral particle is that because most of the instruments which detected particles are based on Coulomb's force. So Coulomb force only applies to charged particles, and neutron is a neutral particle. So it was detected very late by some other method. So this led to the failure of the neutron-proton, the proton-electron theory again was now the failure led to discovery of new particles, and the neutron was discovered, and finally we have the present idea about the constituents of the nucleus, and that is nothing but the well-known neutron-proton theory. So the neutron-proton hypothesis. So we have the neutron-proton hypothesis. Actually now it's not a hypothesis, it is a theory, because it has been able to prove all the experimental observations that the proton-electron theory could not prove. So we saw certain things for the proton-electron theory. We had written the points without understanding them, because I'll be explaining in your next class. It will take some time. So today please consider it as an introductory class. So we found that in case of proton-electron theory, the statistics which we will learn, then the magnetic moment and such points that we had written, moment, magnetic moment. Then we had a problem with the uncertainty principle also. So these were certain points which could not be explained by the proton-electron theory. But instead of the electron, when we keep the neutron there, all these could be explained, and so the proton-neutron theory is for here to stay. So now we have this picture of the nucleus, which we already know that nucleus consists of the protons and the neutrons. So we have excuse me, proton and neutron. So now we know that this constituents of the nucleus are protons and neutrons, except for the hydrogen where we don't have a neutron, we have only one proton. All other elements have both protons and neutrons. And let us now start the study of nuclear physics based on this basic introductory points. So we know that with any nucleus we can associate a number called the atomic number. It is denoted by Z, and it is nothing but the number of protons. We have N, which is the number of neutrons. Then we also have A, which is the mass number. So what is Z? Z is the atomic number. And A is N plus Z, which is the sum of the number of neutrons and protons. And this is nothing but the mass number. We call it the mass number. So you know all these things. I'm just trying to take you down memory lane so that you remember. So this is the mass number, and you see the neutrons and the protons, they are constituents of the nucleus, and we call them the protons and neutrons. We also call them the nucleons. That means particles inside the nucleus are nucleons. And so I can also write A is what? A is the number of nucleons. So these are certain things. So usually we write it like this: A Z, or you write it as in some books they write it like this: A Z. Sorry, if I put element X, if I write this is not correct, as X, you put the atomic number on the top and the mass number at the top and the atomic number at the bottom, either on the left or the. This is a way how you denote a nucleus. So as we know, the electron, proton, they are very small particles. You see, the nucleus is a totally quantum mechanical particle. So it's a totally quantum mechanical particle, and so since it's a quantum mechanical particle, it's a very small world, and there's always an element of uncertainty because uncertainty principle applies everywhere. So today I'll stop my introductory class here, and we'll do the real nuclear physics from our next class. Thank you very much.